In this video, we're going to solve an example from Hibbeler's textbook, Statics. The example will be 7.1, and it relates to the chapter on internal forces. In this example, we're given a beam that is supported by a hinge on the right and a roller on the left. The beam experiences a 9 kilonewtons meters bending moment about at the hinge and experiences a 6 kilonewton vertical force acting at about 3 meters from the roller. In this problem, we have to determine the normal force, the shear force, and the bending moment that's acting just to the left of that 6 kilonewton force and just to the right of that 6 kilonewton force. In other words, if our force acts along this line, we want to find the internal forces that are just to the left of that line and immediately to the right of that line. For simplicity, we're going to call the roller point A. We're going to call our point just to the left point B. We're going to call our point just to the right point C. And we're going to call our hinge point D. So, whenever we have a problem like this to solve, where we're going to find the internal forces acting on a structural member, the very first step is to draw a free body diagram. So we'll do just that. From the given data, we have a beam, which will be our structural member. Notice that when we're trying to find internal forces on a structural member, our free body diagram has to be of the entire structural member, not of a point in that member. Let's look at the forces. We are given a 9 kilonewtons meters moment acting on the right side. You can hear that noise, that's my cat playing with something. We have a 6 kilonewton force acting at 3 meters from the left of the beam. Point A is a roller support, which means that we will only have a force in the vertical direction, which is the direction normal to the surface of that roller. I'm going to call this force AY. And point D is a hinge. Now we know that hinges provide supports in the vertical, provide reactions in the vertical and horizontal directions. I'm going to write a couple of dimensions. And there we have our free body diagram. Once we've drawn our free body diagram, the next step is to apply the equations of equilibrium to try to solve for any reactions or external forces. In this problem, we have 3 unknown reactions: AY, DY, and DX. But since we want to find internal forces, remember we're eventually going to use the method of sections, so we're going to make a cut. We can always choose to use one of those sections. We don't need to use both sections when we make a cut. Now what that means is that for this particular problem, we only really need to find the reactions at one of the sides. In this case, I'm going to choose the easiest side, which is A. In this case, there are no unknown x reaction forces, so there's no need to use sum of forces in the x direction. We also cannot use sum of forces in the y direction because we'll end up with 2 unknowns that we can't solve. So we can't use our sum of forces in the x direction or our sum of forces in the right direction. I would say we can use our sum of moments. In this case, if we choose to take our moments about the roller A, we will not be able to use that to find this force. Instead, we can take our moments about point D. Why do we do this? If we take our moments about point D, we are eliminating dy and dx from our equation, which means that we'll end up with only one unknown, which is ay. So, we know that our equations of equilibrium tell us that the sum of moments about point D have to equal 0 in order for this to be a static system. So what are those moments? Starting from left to right, I see that I have a force AY, whose magnitude is unknown, acting at a distance of 9 meters from point D. Notice that this force will cause a rotation about point D in the clockwise direction, which means that it will have a negative moment. Moving on, we have a force of 6 kilonewtons acting at a distance of 6 meters from point D. And this force will cause a counterclockwise rotation, which means that we will assign it a positive value. Moving towards point D, we don't have to count dy or dx because they are causing no rotation about that point, but we do have a 9 kilonewtons meters moment acting on it. Notice that this rotation is counterclockwise, so we will give this value a positive number. And following our equation of equilibrium, the sum of these three numbers has to equal 0. Now when we look at this equation, we have one unknown and all of our other values are known. So let's go ahead and solve for AY. In this case, AY will be equal to 36 kilonewtons meters plus 9 kilonewtons meters, that should be 45 kilonewtons meters, divided by 9 meters, that should be 5 kilonewtons. Now that we have that force AY, we can write it back in our free body diagram. So, we applied our equations of equilibrium, and we found AY. However, that's not what the problem asked us to do. In this problem, we were asked to find the internal forces at points B and point C. In order to find internal forces, we have to use the method of sections. In this case, we will make a section cut right where this force is acting so that we can find the forces at point B. We can make another section cut immediately after this force so that we can find our internal forces at point C. But let's take it one step at a time. So let's move on to step number 3. Step number 3 is to select a point that we want to analyze and then make a section cut right at that point. I want to start with point B. In this case, since we want to analyze point B, our section cut has to go through that point. Now, we know that point B is immediately to the left of that 6 kilonewton force. Because it is immediately to the left, then the distance between point B and that 6 kilonewton force can be negligible, which means that our section cut will be at approximately 3 meters from point A. Cutting this section will give us the following subsection. where we will have point A on the left, point B on the right, and a distance of 3 meters between them. From our free body diagram, we know that there is a reaction force of 5 kilonewtons acting at point A. But since point B is immediately to the left of the force, then we don't really have any other forces acting on that section. So now that we've identified all of our external forces, we can start to identify our internal forces. If you remember from the lecture video, we will have 3 internal forces: a normal force, a shear force, and a bending moment. If you don't remember the sign convention, have a review of the lecture and of the textbook. But remember that we're always going to take tension forces as positive when it comes to normal forces. We will take our shear force to be positive if it causes your section to rotate in the clockwise direction. And we will take our moment to be positive if it bends your section into a smile, as one of my students put it. Always assume that your forces are positive. That way we can get the right sign convention. So if our normal force were to be in compression, we would get a negative number, which is okay. That's the answer we're expecting. So after we've made our cut and we've identified the internal forces, the final step is to solve for those internal forces. Now this system is in static equilibrium, which means that at any point in the system, our equations of equilibrium should apply. Let's start with the sum of forces in the x direction. In this case, we only have one force in the x direction, and that's the normal force. So now we have that the normal force in this system is 0. Let's move on to our sum of forces in the y direction. In this case, we have a 5 kilonewton force in the positive y direction and an unknown shear force in the negative y direction. Our equations of equilibrium tell us that the sum of these two values equals 0. And from this, we can say that the shear force is equal to 5 kilonewtons. So there we have our shear force. Now we can take a sum of moments and for this example, the best thing to do is to take the sum of moments about point B. So from point B, we have a 5 kilonewton force at a distance of 3 meters from that point. This 5 kilonewton force will cause a clockwise rotation about point B, which means that we'll give it a negative moment value. Moving on, we have an unknown internal bending moment in the clockwise direction, in the counterclockwise direction, so we'll give it a positive value. Solving this, we get that the bending moment at point B in this beam is equal to 5 kilonewtons times 3 meters, or 15 kilonewtons meters. In this example, all three of our internal forces and moments had positive values, which means that the directions that we assumed were correct. Don't forget to mark your answers. So there we have it. We solved for the internal forces at point B. However, the problem also asked us to find internal forces at point C. So, steps 1 and 2 won't be changed. However, for step 3, instead of taking our cut at point B, we now have to take our cut at point C. So let's do just that. In this case, we have our beam with points A, B, C, and D, and we will take the cut at point C. Now point C is immediately to the right of your force. And again, because the force is a point value and there is very, very little distance immediately to the right, we can take that the distance between point A and point C is also 3 meters. This lands us with the following section. In this case, we have a reaction force acting at point A. And since point C is immediately to the right of your 6 kilonewton force, then we also have to include this 6 kilonewton force. At point C, we have our internal forces and moments. And as we did with the earlier example, let's assume that our internal forces and moments are in the positive direction. Now the final step in this problem is a repeat of what we did for point B, which is to apply the equations of equilibrium in order to solve for those internal forces. Again, starting with the sum of forces in the x direction, we get that the normal force at point C equals 0. Now, moving to the sum of forces in the y direction, we have to include not only the 5 kilonewton reaction from the roller, but also the 6 kilonewton external force. Solving for your internal shear force gives us a value of let's see, 5 minus 6, negative 1 kilonewtons. Now what does this negative mean? This negative means that the shear force, instead of acting in this downward direction, is actually acting in the opposite direction. Now, in order to keep a consistent sign convention, I would just leave this number as a negative value. I wouldn't go back and change the direction of the arrows, just leave it as negative 1 for now, at least for this example. Taking the sum of moments about point C, we have a 5 kilonewton force acting at a distance of 3 meters from point C. We have a 6 kilonewton force acting at a distance of almost 0 from point C, so it won't cause any rotation. And then we have a bending moment. So writing all that down, we'll have our 5 kilonewton force times our 3 meters distance, negative because the rotation is clockwise. We'll have a 6 kilonewton force times both, and we'll have our internal bending moment, M sub c. Solving for our bending moment, we get that M sub c will equal 15 kilonewtons meters. And don't forget to mark your answers. And there you have it. That's how you find the internal forces at two different points in this beam.